So, artificial intelligence becoming a bigger talking point in the weather modeling community, and Google this year has launched a new artificial intelligence model that can try to predict where hurricanes are going to go and how strong they're going to be. Joining me now, Olivia Graham, a manager of the Weather Lab at Google. Thank you so much for joining me today.
Thank you for having me.
So tell me, Olivia, when did Google decide that predicting the weather was an area that they really felt that they could put their stamp on?
Yeah, I would say our teams are so curious. And what motivates them is finding these big problems where it seems like things might not actually even be possible. And this was a question that our research teams had. We know that AI is so good at learning from large data sets, at inferring patterns and predicting forward what might happen next. We've seen that with large language models, which are trained on a vast amount of text and learn from that how to respond to all kinds of user questions. And so with weather, there was almost this unanswered question. Things had been done a specific way for decades. We've got these amazing models produced by NOAA, by the European Center for Medium Range Weather Forecasting, that use the laws of physics to predict forward what the weather is going to be. And our teams asked themselves, could we train a model based on decades of historical weather data to, even without access to those underlying laws of physics, infer patterns and predict the future?
So it's doing a lot of pattern recognition.
It is, yeah. What you hear in the community, meteorologists describe these AI models as being more data-driven. So we haven't explicitly told them what the rules are, but they're learning that for themselves, essentially.
They're learning that. So to create something like that, that's learning for itself and recognizing patterns, what type of people with different skill sets do you need to have in the room to develop something like that, and what's the timeline?
Yeah, so what is so special about being at Google Research and Google DeepMind is that we have both these technical experts who are computer scientists, machine learning experts by training, as well as these domain experts. So people who have a background in meteorology and atmospheric sciences. And in my opinion, where magic really happens is when you can marry the two. When you have the domain expert saying, look, this is a really tricky problem in my field that we haven't been able to solve, and here's a great data set. And the machine learning scientist goes, oh, well, I could train a model, and maybe we can make something happen together. So it's a team with a pretty diverse background, but I would say those are the main profiles that we have.
Now, traditional weather models, like you said, it's the physics of the weather. It's like fluid dynamics. It's, when we're going through meteorology school, there's a lot of math and physics. But your models are learning pattern recognition.
Correct.
So what exactly is in that data set that they're looking through and sorting through and learning as we get new storms over time? What's in that? What are they getting from the European Center?
So we benefit a ton from the work that Met agencies around the world have done to collect high-quality data sets. We couldn't do our work without them, right? We couldn't have weather models if there weren't all of these observations of what's going on at the atmosphere at all points in time. And so when we have trained our models, we've leveraged both a data set that's called ERA 5. So that comes from ECMWF, the European Center for Medium Range Weather Forecasting, and it's a 50-year reanalysis data set that is really high quality and has sort of unlocked this revolution in weather forecasting because machine learning scientists were able to train models with it. And with our new experimental cyclone model, we're using not just that data set, but also an archive of past hurricanes. So the model really learns to optimize its performance for those weather events.
So then the past hurricanes, we know their path, their strength. Do we know what the sea surface temperatures were or anything else at the time that those storms happened? Because I'm just, I'm just trying to picture in my mind, if a storm is here and a storm 20 years ago is there, what differentiates your model being able to figure out, okay, where is Aaron actually going to go?
That's a good question, and I would say it's a function both of what has been observed in the past, but also current conditions. So we train the model, like I said, on 50 years of data, plus cyclone-specific data, and when we run the model at inference time, it's looking at all of those variables that you just mentioned. So, thinking about it as a human, it's all the work that meteorologists do to ask what are current conditions based on what I know about how past systems have developed. What does that tell me about how this new system that I haven't seen before is going to evolve and change over time?
So then does it get info from the hurricane hunters and plug that in, or does it get weather balloon releases and plug that in, or is it like what all is going into
what does it get in real time?
When it initializes, models initialize. Traditional models, a lot of them are every 6 hours or 12 hours.
Yeah.
Yours is much more frequent, right?
We only run it every 6 hours.
Every 6 hours.
And that's partially because we are dependent on HRES for input conditions. So the European Center for Medium Range Weather Forecasting does all of this data assimilation from those diverse data sources, the weather balloons, radar, all sorts of things, and then outputs the current state of the atmosphere. And that's what our models use as a starting point. And so as we think towards the future, we can imagine a world where maybe these new models, new generations of models, will be able to incorporate those observations directly from the hurricane hunters, getting the most fresh and up-to-date measurements so that they can make more frequent predictions. But we're not there just yet. That's sort of the next chapter, maybe,
but
of
an
where this work could go.
Amazing feat that you've already accomplished. So talk to me about the transition of going from the first modeling of doing the nowcasting to now, and what you all at Google hope to accomplish in the future with dabbling in weather research with AI.
Yeah, so figuring out the art of the possible is what we do here at Google Research and Google DeepMind. And there's so many questions that the community is now coming back to us with. So our first models were somewhat simpler. They could predict precipitation, but only for the next 12 hours, and only in regions with dense radar coverage. So the US, Europe, Japan, that's kind of it, looking at the globe. And so as we've continued to progress in our weather research, we've found that more and more is possible. So with the first milestone of nowcasting, people asked, well, could you really have a successful 14-day forecast? Is that something AI can really do? And turns out it is. That was a deterministic forecast. And so the next question was, could you have a probabilistic forecast? Could you show an ensemble of ways the weather might evolve? And that was the next milestone in our work. Then we kept hearing from the community, oh, well, these models can do hurricane tracks, but they're not so good at intensity. They kind of hedge their bets. The model, when you train it, it's incentivized to not want to be too wrong too often. And so it can sort of give you the average guess rather than really capturing the extremes. And so with this project, we wanted to understand, given the severity of hurricanes, given that we're seeing more and more of them every season, and given the huge human impacts that they have, could we actually push the state of the art on intensity as well? And so it's kind of a continuous conversation with the community as we understand what are the big challenging problems that need to be solved, and are we well positioned to help advance the science and hopefully solve them.
Now, along the way, to improve your models, you got to get feedback. So that's part of a new partnership with NOAA, the National Hurricane Center, is to get feedback. How often are they looking at your data? How often are they giving you feedback? And what type of feedback over this hurricane season do you expect to get from them?
Yeah, so we've been working with them since almost the beginning of this project, because we knew that to really have confidence in our results, we wanted to be working with experts. It wouldn't be enough for us to say, look, we evaluated our model and we think it's pretty good. We wanted someone that we could really trust to help us understand whether what we were seeing was consistent with their deep understanding of the space. And so they've been phenomenal partners. We signed a cooperative research and development agreement with them. So they've actually been in the loop since the beginning, helping us to shape the product and the research. They've been phenomenal collaborators. And what's been amazing to see is as forecasters put out warnings and watches, they're beginning to actually cite us to say, maybe the ECMWF model says this, but the Google model says this. And we're going to continue to work with them over the course of this season to understand how well our forecasts performed, whether they were operationally valuable, and sort of where we should take this from here.
So are they giving you any feedback on Aaron yet? Or is it we're looking at it and we're evaluating it as another one of those scenarios that Aaron could do?
Yeah, more the latter. It's almost too early to say, right? It's early days for Aaron. It's still developing. And so we're seeing that they're consulting our forecasts. They're using that to inform their decision making. But it'll really be we think that it'll take until the end of the season for us to really have a holistic understanding of just how well the model did.
Right. And a lot of these hurricanes, of course, forecasting rapid intensification has been one of those,
grand challenges.
Yeah, grand challenges because it's like Goldilocks and the Three Bears. You got to have low wind shear, you got to have humid air, and the warm water is like, sometimes these storms we know they can rapidly intensify and then they just take off. In addition to the strength of these storms, how is your model able to predict kind of the wind field, how big they'll be? And do you think that at some point you could also dabble in storm surge and how much rain a hurricane can produce? Because historically, water is more deadly than winds in these storms.
Right, it's the storm surge that really can devastate communities and can create these sort of terrible effects. That is such a great question. Truly, such a great question. And that's what we're trying to understand, are what are these big problems where we might have an opportunity to come in and really build something that is very, very useful for the community. I would say we've got some explorations on wind fields, nothing that is yet at a point where we're ready to ship it and share it with the world, but we continue to think about, what else could we do in this space, and what are the needs of the community, what are the needs of forecasters, and can AI support in those spaces?
Excellent. So, to be announced.
To be announced, right.
The seedlings have been planted, so to speak.
Exactly.
Do you feel, whether AI modeling relies on training itself on past events, do you feel that as our climate warms, that it might struggle a bit to forecast the extreme? Because 50 years ago, our average temperatures of the ocean look different from what they'll be 10 years from now?
So what do we do, given that these models are learning from past patterns, as future conditions change? How do we know what their performance will be like? Such a good question. And I think what's really exciting about these data-driven models is that we actually have the ability to fine-tune. They're pretty flexible and extensible. And so with a numerical weather prediction or physics-based model, where it's pretty time-intensive to rewrite the underlying rules, with AI models, you are able to actually fine-tune and to say, hey, here's a data sample from the past 1 year or 2 years, learn from the past 50, but really optimize for the last 2 years of conditions that we've seen, or optimize for a specific variable. And so
weighing that a little bit heavier.
Exactly.
Right.
Exactly. The models you can sort of almost put your fingers on the scales a little bit and tell it what success looks like, so that it can optimize for those conditions.
I have two last questions for you before we step over to the board and kind of look at the model and talk about Aaron a little bit. How do you hope, looking maybe 2 years down the line, that this will aid in decision makers? Do you feel that it will be something that they can use to help make decisions of where evacuation should be, or whether I need to be concerned about a storm? And then also looking even further down the road, do you feel as an organization that this could one day take away meteorology jobs, or do you feel like there always will still need and be a place for that human intuition of where storms might go?
Our goal with this work is to create new tools for meteorologists like yourself so that they can better understand how phenomena might develop, where hurricanes might go, how intense they might be. And that's really been the goal of working directly with the National Hurricane Center and other amazing partners around the world. To name a few, the Bureau of Meteorology in Australia, we've got partners in Japan. We know that these trusted agencies are the ones that people turn to in times of crisis. They're the ones who have the mandate to tell people what they should do and how they should respond. And in times of crisis where the stakes are so high, we want to be sure that those decision makers have the best data that they can possibly have access to. And that's sort of been the thesis of this work. Can we use AI to improve the tools and then empower meteorologists with those tools? Because a forecast at the end of the day I mean, you can have the world's best forecast, but if no one understands it, if no one can explain what that means for people, it's not worth very much. And so the partnership we've had with the NHC, with Met agencies around the world, we've learned so much from them, and we're really looking forward to continuing the work with them.
So you still need the human intuition for the impact.
Absolutely,
But
yes.
the data that you can potentially give with AI is the ceiling. There is no ceiling in terms of where it could head one day.
I don't think so. I mean, even just with this first milestone of work with our experimental cyclone model, we're seeing these crazy jumps in accuracy that rival even the best models that have been specialized for the Atlantic basin. This is, of course, historical analysis, looking at past years, but it blows my mind that when I talk to scientists, when I talk to our colleagues at the National Hurricane Center who've spent their lives studying hurricanes, that they can't believe how quickly this is moving and how quickly we're starting to see improvements. And so my hope is that this is just the beginning and that we'll continue to see field-defining breakthroughs and rapid progress in this space.
So what are we looking at?
So this is Weather Lab. It's our new interface where you can explore the outputs of our AI-powered tropical cyclone model, as well as the outputs from other models. So we wanted to really build in public this season and to give people the ability, whether they're meteorologists or just weather geeks, to actually follow along and to see what our model is predicting compared to what other models are predicting.
So I see over here, we've got your experimental model right here. We also have like the European ensemble models and everything. But this is showing Aaron's progression to major hurricane. But then you have a new feature where you can see the different ensembles. Can you talk to me about how many of those that you have on every model run?
Yeah, so for every model run, we produce 50 ensemble members. Not every one of them will necessarily predict the cyclone, right? If you pan over here, let me see if there's anything else going on. Okay, no, it's just, exit out of that. There we go.
There we go.
So we can see, this is not a named storm, but the model thinks that there might be some activity around here. And so up to 50 for each hurricane is what you would expect to see. And here for Aaron, if we turn on those ensemble tracks, and you're the meteorologist here,
yes.
So you'll let me know what you see. But it seems to me like they're all pretty much, in agreement. There's not a super wide spread.
Right. So yeah, they are in pretty good agreement. I would say, ensembles and traditional weather models, they're looking at, okay, if we have a slight perturbation or change in our initial conditions, what would it do to it? Is that what your ensembles are doing too?
Exactly.
Okay.
Yeah, so it's a similar way of modeling the uncertainty. So of trying to capture the fact that we know that small changes can result in very different outcomes. And so when we are running our model, the way that we create ensembles is just like you've said, sort of reflecting that uncertainty and baking it into the model run.
So again, just so I can, and I see wind speed color on here as well, just so I can get it right, you all do get some kind of analysis from the European Center of here's what the conditions of the storm are right now, and is it the ocean temperatures too, or is it just here's what the storm looks like and here's where it's positioned?
I'd have to get back to you on ocean temperatures. I don't know that we have an ocean model incorporated, but we definitely get all atmospheric current conditions.
So then this has, I'll kind of zoom in on, the touch screen. So you have wind speed in here. Let's put the ensembles. So they're all showing wind speeds. Didn't you say you got a question from the Hurricane Center about if it takes this track, does it mean one thing or another for wind speeds?
Yeah, so they actually, what's been amazing about working with the National Hurricane Center is that they are such experts in this space. They've been wonderful collaborators, and they've come back to us and said, hey, could you help us understand what your model is saying in this specific set of circumstances? And so before, we only had, the ensemble tracks were in all the same color. You could see that they might have different predictions for max wind speed here, but you couldn't really visualize that information. And so the NHC came back to us and said, hey, if you just allow us to color code this, then we can understand not only what the spread of the tracks looks like, but also how the intensity and wind speed might be correlated with the position of that track. So this was something that they had requested that we were really excited to be able to deliver for them.
It's like a new dimension of
Yeah.
looking at it. And I do see your chart, so that's great. So you can actually see the different spread in the models of here's what the wind speed is they're predicting, and here's what the pressure, how it's going to drop.
Exactly.
Oh, and you got
so you
your-
can click
okay.
into any ensemble member and ask, come on, touch screen. There we go. You can click into any ensemble member and actually see at this position what is the predicted wind speed, category, and
Wow.
where will the ensemble member evolve.